Okay, so this is a heating curve for water. This is showing water going from the frozen state all the way to the gas state. So we've got temperature in degrees Celsius on the y-axis, heat added on the x-axis, and this, I believe, is for 1 mole of water. Starting at negative 25, as you warm it up, as you add heat, the temperature increases till you get to the melting point. At the melting point, all of the energy that you're adding goes into melting the water. Once it's all melted, the temperature begins to rise again until the water will boil. And at that point, the temperature stays the same until all the water has been transformed into a gas state, and then the steam can get hotter and hotter. So we can calculate the amount of energy needed to go from any one point on this curve to any other point. It's not really a curve, is it? It's a series of straight lines. Straight lines are nice because you can calculate them. So 1, 3, and 5 are going to use the Q equals MC delta T equation that we studied back in chapter 6, where you heat something and the amount of heat needed to change the temperature depends on the mass of the substance, how much you have, and it depends on the change in the temperature. For the flat sections, the horizontal portions where you have fusion and vaporization going on, you just use the heat of fusion or the heat of vaporization as a conversion factor. So you find each of the line segments and then you add that energy together and you get the overall. So we'll do an example. Calculate the amount of heat needed to take 1 mole of ice at negative 25 degrees Celsius to steam at 125 degrees Celsius. And this is sort of a problem that could show up on an exam. So it's often helpful to draw, to just kind of sketch a heating curve. And so you're going to have some flat places. Doesn't need to be to scale, the slopes of the lines. We're not going to calculate anything off of this, but just help us see what's going on. So this is energy added on the x-axis, and this is temperature on the y-axis. So the problem tells us that we're starting at minus 25. And what's the melting point of water? 0. And what's the boiling point of water? 100. And then the final temperature, no, we do care. The final temperature is given in the problem, 125. This problem is going from solid below freezing to gas above the boiling point, and so we've got a bunch of line segments. You could also do, ice at 0 to water at 59 degrees or something like that. Any combination. So, yeah, you got a question?
Yeah, can you figure the whole change all the way from the negative 25 to the 125?
In one step?
Yes, but just not for the phase changes, for everything else?
No, you can't, because the specific heat capacities are different
Between ice,
for ice, water, and steam.
Five different
So it is 5 calculations, and then you add them together. There's not really a shortcut.
You and my math teacher.
You should just write all one big equation like Q needed equals Q1 plus Q2 plus Q3 equals 1 all that, right?
You could. I don't necessarily recommend that.
Okay.
It's easy to get lost.
Yeah.
So these are tedious, but the math is simple, and the concept is pretty straightforward once you can see it. So we draw this diagram, making sure that we've got flat places for phase changes and slanted lines for temperature changes. And then I think it's helpful to number these so that we don't forget what we're doing. So I'm going to call that one 1, 2, 3, 4, and 5. So we're going to calculate the energy for each of those. and we're going to use Q equals MC delta T. That's going to be used for transitions 1, 3, and 5 because the temperature's changing. And then for the others, we're going to use delta H for 2 and 4. Delta H of fusion or delta H vaporization.
Which is pretty easy, because you're just getting.
Pretty easy, yeah. Yeah. So let's start here. So let's do number 1 first. You don't have to do 1 first, but just habit, I guess. So step 1 is increasing temperature, and so that's Q equals MC delta T. So Q is the heat that we're calculating. What is the mass for this problem? 18.02 grams, because we have 1 mole of ice. So we're going to need the molar mass of the water and convert to grams. But we've done that before, so I'm not going to write that out. So 18.02 grams times the specific heat capacity. In this transition, this is frozen. This is a solid, and so we need the one for ice. So 2.09 joules per gram degrees Celsius. And then we need the temperature change. Temperature change is always the final temperature minus the initial. So for this line, what's the final temperature? 0. And what's the initial temperature? Negative 25. Okay, so 0 minus 25 is plus 25. Right? So then let's calculate that. 18.02 times 2.09 times 25. 941. That should have 3 sig figs. And the unit there is going to be joules, because the grams cancel and the degrees Celsius cancel. And the units are important because some of these are going to be in kilojoules, and if we don't take that into account, it'll be messed up. Step 2 is the ice melting. So we're just going to use the heat of fusion. So for that one, we've got 1 mole of water times the heat of fusion, 6.02 kilojoules per mole. And so that's just 6.02 kilojoules, because the moles cancel out. Step 3 is a Q equals MC delta T again. Q equals the same mass of water, 18.02 grams. But now I need to use the specific heat capacity of liquid water, which is higher, 4.18 joules per gram degrees Celsius. And I need to use the temperature change for line segment 3. The final temperature is 100. The initial temperature is 0. 100 minus 0 is 100. So I do that one. 18.02 times 4.18 times 100. So 7,532.4 joules. And that one again would have 3 sig figs. These temperatures here, the 100 and the 0, those would be exact. The final and initial would be not exact. So I guess technically this should only have 2 sig figs. Okay, so number 4 is an easy one again. Boiling. So we're going to use the heat of vaporization, which is 40.7 kilojoules per mole. So that's just 40.7 kilojoules. And then 5 is Q equals mc delta T again. So the mass, 18.02 grams, times the specific heat capacity of steam, 2.01 joules per gram degree Celsius. And then the temperature change for this segment. The final temperature is 125, the initial temperature is 100. 125 minus 100, that's 25 degrees Celsius. (905.5 joules). Okay, any questions? I see a lot of interesting things when I give this as a show your work problem on an exam, and one of the things students will sometimes do is they'll take the 125 and the 25 and they'll use that as the temperature change for everything. Well, that is the original initial temperature and the final temperature, but it is not the temperature change for liquid water or for the steam or for the solid. And you have to look at each of these individually. You should know the boiling point and melting point of water. Anything else, it would be given to you somewhere, either in a separate table or in the question. So you might have to look up the boiling point and the melting point. So to find the heat, we have to add all of these together. We've got some with kilojoules and some with joules. And I think kilojoules is going to be a better unit to use because, like here, we've got 40.7 kilojoules. That's already a relatively big number. And so when we add more, it's just going to get larger. And so I'm going to convert all of these into kilojoules. And we'll do that just by, you can write it out the long way, or you're moving the decimal point 3 places. So 0.9415 kilojoules. This one's 7.5324 kilojoules. And this one is 0.9055 kilojoules. The other two are already in kilojoules. So I'm going to add these up. Yeah, I screwed that up. Can somebody just shoot me the answer? You got what? 56.099. That looks about right. So that would be kilojoules. Yes, I messed up with my calculator. Significant figures now we're adding, and so we're looking for the fewest number of decimal places. This one over here has 1 decimal place. That's got 2 and 2 and 2 and 2. So 1 decimal place is the smallest number of decimal places. And so then we're going to report this answer as 56.1 kilojoules. Any questions?
It's the amount of or amount of decimal places and all this. What is it again?
So number of decimal places in these numbers that we're adding together.
2 decimal places.
2, 2, 2. Most of them are 2, but this is only 1 decimal place. So that's going to limit it.
Right there. Okay.
Yeah. And when it says 1 mole, it's going to be really just dumb if you say, well, that's 1 sig fig. So it's just a sloppily worded problem, but it'd be better to say exactly 1 mole. We used to do calculations like this just kind of for fun and see, well, could you lose weight just by eating ice, right? So, you know, you got ice from the freezer and then maybe it's -5 degrees Celsius and you eat the ice and then you have to warm the ice up to 0 and melt it and then warm it up to body temperature, and you can calculate how many kilojoules of energy it would take to heat up the ice, right? And then you can calculate how much energy it takes, how much you get from burning a pound of fat. And I'll just tell you, it would take way too much. It's not a viable option. But it was a fun thing to talk about. Any questions?